Hi, in this video we're going to talk about how to implement min heap. We'll start with the basics and insertion. Before we actually get into the implementation details, I want to say this, which I said before, is that in order to study any of these data structures, it's very important that you can see what's going on. And in order to see what's going on during any of the operations, it's important that you draw pictures. So get some papers and pencils, and as we step through how things work, draw pictures to help yourself visualize what's happening. So the insertion operation in the min heap, basically what it does, it should, given a piece of new data, it should find the right place to put it in the heap. And the right place is one that satisfies the two min heap property, right? The first one is just shape property that after the insertion, the min heap must still be a complete binary tree. And then the second property is the heap property, and that is that each element is still smaller than its children after the insertion of the new data. Okay, so the strategy for finding the right place then is, first, we'll put the new data at the end of the heap. Now, what this does is that it will satisfy the shape property, assuming we start with a complete binary tree. We will still end up with a complete binary tree, right? But most likely it will not satisfy the heap property, because if we just put the data always at the end, then there's a good chance that it's smaller than its parent. Okay, so how do we deal with that? So the way we'll deal with that is that we'll compare the new data to the parent's data, right? If it's smaller than the parent's data or key, we'll move the parent's data down and kind of conceptually move the new data up to the parent's place. So we're kind of doing a swap here. So we'll just keep repeating this until we find the right place, right? Until we find the place where the new data is bigger than its parent's data. So this process is called percolating up. So to help you to see how the algorithm actually works, let's use this very nice visualization tool, and we'll insert just three numbers, 5, 9, and 3. Okay, so the first number we enter is 5. So we say insert, and well, this is very simple. There's really kind of, we insert one node, and then remember we put the first element at index 1, now get index 0, and that's it. Okay, so the next piece of data we want to enter, we will want to insert is 9. So 9 will obviously add a child, put it at the end of the heap. We'll put a 9 here, and so in the tree form it's going to appear as the left child. So let's, the animation show the tree form first, and then we put it at the end of the heap in the array. Now, then the next thing it's going to do is it will compare 9 to the parent, right? And to see if it's bigger than the parent. If it's bigger, then it's in a good place. If it's not, then you'll have to swap them. But 9 is bigger than 5, so that's great. There's nothing else to do here. Okay, the next piece of data, we'll enter 3. All right, so what happens with 3? Well, we'll put 3 here, and then the 3 becomes the right child of 5. So let's do that. And we'll put 3 here. Now in this case, 3 again must be compared with its parents to make sure that it satisfies the heap property, and in this case it does not, because 3 is smaller than 5, and that's not good. So what must happen then is we'll swap 3 and 5. We'll percolate 3 up the tree to its parent. Right, and this is what happens here, and then we are basically done. Now, to make sure you understand this, I think it's now your turn to try to do a little bit of insertion yourself. So on top of what we've done already, try to insert the number 7 and then 1 into this min heap. Now, I know it's probably tempted that you just use the visualization to see some pretty animation and think that you understand this. Please don't do that. Do this by hand on a piece of paper, and then once you're done, you can use the visualization tool to verify your results. Okay, assuming you've done it yourself, let's look at this together just to make sure we are on the same page. So let's insert 7. So what happens with 7 is, yeah, it has to start a new level. Basically, if we start on the left side, right, and in terms of the array, it appends to the end. Now it has to compare with the parent, and 7 is bigger than 9, so we have to kind of pull 9 down and percolate 7 up. And then that's it. We are kind of done. We don't have to keep going because, well, I mean, it will compare 7 and 3, but we don't have to swap, so that's great. We're done. Now, 1 will be slightly more interesting, and so we put 1 at the end of the array, and in the tree, it's here. We compare with its parents. We have to put the parents up, percolate 1 up. And now we have to keep doing this, right? There's a chance, and as a matter of fact, 1 is smaller than its parent, 3, so we have to swap these two again. So now 1 is at the root, and there's nowhere else to go, and this tree is a min heap again. Now let's look at the actual code of min heap. So we'll start with the very basics, not even insertion itself, the initializer and the string and also the size of the heap. So for the initializer, it's very simple. We are going to have a private attribute called heap that will act as our array, or well, it's a Python list that will store all the data that's being inserted. Now, remember our first the element at index 0, we don't use it for anything. So when we initialize this array, we'll initialize it with a none at index 0. Now, the next thing we'll do is, it's very useful to see how many things are in the min heap. So we'll override the length method. The number of elements in the heap is what's in the private array minus 1, right? Because the first one doesn't count. So if we start with an empty min heap, the length of the private underscore heap is 1, and 1 minus 1 is 0. So we have nothing in the heap, right, as far as the client code is concerned. So that's what this minus 1 is. Now there are there's some implications when we do it this way, right? That the first element is going to be self underscore heap 1, right? Not 0, again, not 0. And then the last element will be self underscore heap, the length of self, and that is basically the length of heap minus 1. That is the last element. Okay, make sure you remember these two because that's very important as we talk about the implementation. And finally, we override the thunder string to print out both the size and what's in the array, and that's very useful for debugging. Next, let's talk about how insertion actually worked. I already typed up the code here, so let me explain it line by line. So Insert itself, the first thing we do, given a new piece of data, is that we'll append it at the end of our array. Okay, so again, this will satisfy the shape property, but not the heap property, right? And then to fix it so that it satisfies the heap property, we'll do the percolate up. Now, what happens in percolate up is first, we know the data that likely violates the heap property is the one that we just put at the end of the array. So we remember that piece of data, and then because we're going to have to compare a child and the parent, so we maintain two indexes. The child index, we first start with the thing at the end, right? That's why it's length of self, the last element in the array. And then the parent, as we talked about previously, is the child index, integer divided by 2. Now, just want to point out that in practice, divided by 2 or integer division by 2 is often implemented as a right shift by 1. And that is because it's faster than multiplication. I'm not doing that here just for readability reasons. Okay. Now, so we are going to have to percolate up, right? And that is, as we've seen, it could be one step, it could be two, could be multiple, could be all the way to the top of the tree. So it is a loop, right? And what this loop is we want to make sure the first condition is that as long as we are not at the root yet, if we reach the root, which is the first element, the index 1, if we reach there, then that's the right place, right? So we don't have to keep going if we reach there. And then the second condition that can potentially that will keep us in the loop is that as long as the data itself is smaller, as long as it is smaller than the parent, right? Then we have to again conceptually kind of swap the data and the parent, or actually move the parent data down to the position. Okay, so what actually happens is, while in this loop, so the first step in this loop is, okay, we have to pull or shift the parent's data down, right? And now, while we did previously say, we kind of swap the parent and the child data, we don't actually have to do that in the code, because the child data, which is the new data that we just inserted, we already save it in a variable data, right? So all we have to do is to just assign the parent's data to the child, and that's it. We just keep moving up the tree, doing the same thing. So the new child would be the current parent, and then the new parent would be then the parent of the new child, and divided by 2. So we repeat this process until either we hit the root, or we find that the data is bigger than the parent. So if the data is bigger than the parent, then we can put the data where the child is. So when this loop is done, we basically just assign the data to the child index. And as you know, I like to test code as soon as we have some code that is testable. And in this case, the insertion code is testable. So we'll write a simple test for it. So what this test does is fairly straightforward. We just instantiate a min heap, and then the data we're going to insert into it is kind of the example that we worked out earlier, 59371. And for everything in here, we basically just insert it into the min heap. Now we know what the min heap should look like, right? We still have it here. It should look like 13597 after we are done. So this is what we expect. Then we just make sure that what we expect is what's in the array of the min heap. And then we also know that the size should be 5. I guess this should be the length of the data. That would make it more flexible. So let's actually run this in. There, it's good. So we have some confidence now that our insertion actually works. So this is actually something that we've seen before, right, in a binary search tree, that in the worst case scenario, the new data at the end of the heap or at the very bottom of the binary tree, in order for it to reach the root position, it has to traverse the height of the tree, right? And so because it's a complete binary tree, it's balanced. So the height of a balanced tree is on the order of log of n, where n is the number of elements in the heap. So basically that means the insertion itself is just O of log of n.